Welcome to my presentation on the computational lab. So part one is about OLEDs. This is sort of the energy diagram of the HOMO LUMO of the different layers inside an OLED. You can see here the anode gives out positive charges, also called holes. They move from the anode to the HIL. They then go to the HTL, then to the EML. They can't pass the ETL. They're stopped there, so they're forced to stay in the EML. Similar thing happens on this side, where the cathode, the electrons go to the EIL, then to the ETL, then to the EML, and then they're blocked by the HTL, so they can't pass to the anode. We're going to be evaluating what materials you can use for the HDL and the ETL in this lab. We're going to do that by looking at what the HOMO and LUMO values are for the two organic molecules we're going to look at. To do these calculations, we're going to use NanoHub. We use Orca specifically, and the parameters we need are going to be the 631G basis set and the B3LYP function. So using the XYZ files we provide in the lab, the singlet and triplet energy state can be calculated by using the spin of 1 for the singlet and a spin of 3 for the triplet. You can also calculate the cationic and anionic energy state by using a charge of +1 for the cationic state and -1 for the anionic state. I used a spin of 2 for both these calculations. So here are the values I got from the calculations. As you can see, the lowest value for each is the singlet. This is what we call the ground state. Now, from this, we can do calculations from them, and that's on the next slide. You can calculate the electron affinity and ionization energy. So the electron affinity is the anionic state minus the ground state. Like I said, the ground state is the singlet state. And the ionization energy is the cationic state minus the ground state. So the triplet state has a higher energy for both of them, so it is much less stable. It's not the ground state. Okay, for PA, there's the electron affinity ionization. There it is for PB. Okay, the HOMO LUMO values. These can be found in the output file of the Orca calculation. So here they are. As you can see, this molecule has the highest HOMO and LUMO value, so it's the HCl. And this one has the lowest HOMO LUMO values, it's the ETL. You see in the diagram, the HTL has the highest LUMO and the highest HOMO. And so it's these two. Same with the ETL, the lowest LUMO, lowest HOMO. You see, so that's PA, that's PB. And you can also plot the HOMO and LUMO in VMD, so you can actually visualize the visualize them. So as you can see, in gray is where the ISO value is -0.5, and in blue it's where the ISO value is 0.05. That's the same on this one. Sorry, the ISO surface value. In here, PA, see the LUMO there and the HOMO there. That was the end of part one. So this is onto part two now. Part two is just the stretching of a alpha helix protein that's surrounded by water in like various directions. So stretch mol in NanoHub was used to do the simulation. Then VMD was used to visualize the simulation. Around 3 simulations. First, the protein was stretched 5,000 steps in the x direction. The second molecule was stretched 10,000 steps in the x direction. And the third time, the protein was stretched 10,000 steps in the z direction. And these are the parameters we use in all three of them Its temperature was 300, force constant was 10, velocity was 0.05. So this is the first one. You can see 5,000 steps in the x direction. The molecule is stretched from there across. This is pulling along some water molecules. You can see them, but most of them are no longer bonded to this through hydrogen bonding. This is 10,000 steps in the x direction. You see it stretched much more than the previous one, and there's less and less water molecules you go along, the more it's being stretched, the more hydrogen bonds are being broken. And this is 10,000 steps in the z direction. You can see loads, the hydrogen bonds have gone because we're pulling down on a molecule, which is ripping up more water molecules, breaking more bonds, more hydrogen bonds. Water molecules are bonded to the protein by hydrogen bonding. These weak intermolecular forces keep the water attracted to the protein. But when the protein stretches, most of the hydrogen bonds break, and the water no longer is attracted to the stretched part of the protein. But not all the hydrogen bonds are broken, as you can see. There's still some on there at the bottom. That's the end. Thank you for listening.